Welcome students to the second lecture on determinants. In the first lecture, we have defined what is a determinant for a square matrix and we have investigated certain properties. In this lecture, we shall continue with examining more properties of a determinant and we will try to solve a few problems. If you remember, in property 4, we have seen that if A is equal to A11, A12, A13, A21, A22, A23 and A31, A32, A33, then if B is equal to K A11, K A12, K A13, A21, A22, A23, A31, A32, A33, then determinant of B is equal to K times determinant of A. This we have seen in the last class. Question is, what if all the elements of A are multiplied with K? How does it affect the determinant? Or in other words, what is the determinant of B which is equal to K A11, K A12, K A13, K A21, K A22, K A23, K A31, K A32, K A33. What is going to be the determinant of this matrix? If we expand it in a very similar way, then we get its determinant is K A11 into K A22 into K A33 minus K A23 into K A32 minus K A12 into K A21 into K A33 minus K A31 into K A23 plus K A13 into K A21 into K A32 minus K A22 into K A31. What is this? If we look at each term has 3 K's, 1, 2, 3, here 1, 2, 3, here 1, 2, 3, or in other words, we can take K cube to be common and then what I get, I am not writing it again. You see that this is same as the expression of determinant of A. Therefore, the determinant of B is equal to k cube times determinant of A. If all elements of A are multiplied with k. In general, if A is a n cross n matrix and if all the elements are multiplied by a constant k, then the determinant of the new matrix B is going to be k to the power n into determinant of A. If two rows or columns of a matrix are identical, then the determinant of the matrix is 0. Okay. Let me first verify this. Consider A is equal to A B C X Y Z. So, the matrix is such that two rows are identical. We will show that its determinant is 0. Let us expand it along the first row. Therefore, it is going to be A into B z minus C y minus B into A z minus C x plus C into A y minus B x. This we know. This is equal to A B z minus A C y minus A B z plus B C x plus A C y minus B C x. Now, let us look at the terms plus A B z minus A B z, they cancel each other, plus A C y minus A C y, they cancel each other, and minus B C x plus B C x, they cancel each other. Therefore, the result is 0. Since we did not know the result before, we had to compute it, but once you are an expert and you can see that two rows of a matrix are identical or two columns of a matrix are identical, then the determinant of that matrix is going to be 0. I have shown it using expanding the row, but we know that determinant of A is same as determinant of A transpose. So, if we take the transpose of the matrix, two columns, the first and second column are going to be this identical, and in that case also its determinant is going to be 0. Property 6. Suppose A is a given matrix and we obtain a new matrix B by interchanging two rows or 2 columns, then determinant of B is equal to minus of determinant of A. That is, the value will remain same, but the sign will change. Let me illustrate it. Consider A, B, C, D, E, F, G, H and K. Its determinant is equal to A into E k minus F h minus B into D k minus F g plus C into D h minus E g. We will come back to this, but let us construct B by interchanging 2 rows. Let us take the first and third row. So, the third row now becomes the first row, second row remains as it is, and here we get the first row of A as the third row of B. Therefore, determinant of B is equal to G into E c minus B f minus H into D c minus A f plus K into D b minus A e. Let us now compare with the expression of the determinant of A, which we have just obtained. And now let us consider the signs. G E C had a positive sign, here I get G E C with a negative sign. G B F comes with a negative sign, here I get G B and G B F comes with a positive sign, because minus and minus becomes plus. H D C comes as a negative sign, H D C comes with a positive sign. A H F comes with a positive sign and A H F comes with a negative sign. And then K D B comes with a positive sign here, but here it is a negative sign, and K A E and K A E comes here with a negative sign and K A E comes here with a positive sign. Thus, we see that all the terms are retained, but the sign of all terms have been reversed. That is, if it was a positive here, it is negative here, and if it is a negative here, it becomes positive here. Or in other words, we can say determinant of B is equal to minus of determinant of A. Proved. Property 7, determinant of A B is equal to determinant of A into determinant of B. I directly show it for a 2 cross 2 matrix. I directly show it for A and B of size 2 cross 2, and I suggest that you verify the same way for 3 cross 3 matrices. Let A is equal to A, B, C, D and B is equal to M, N, P, Q. Therefore, determinant of A is equal to A D minus B C and determinant of B is equal to M Q minus N P. Now, A B, the product matrix is equal to A M plus B P A N plus B Q C M plus D P C N plus D Q. Therefore, its determinant is equal to A M plus B P into C N plus D Q minus C M plus D P into A N plus B Q is equal to A M C N plus B P C N plus A M D Q plus B P D Q minus A N C M minus A N D P minus B C M Q minus B D P Q. We see that these two terms cancel, and let us now consider determinant of A into determinant of B is equal to A D minus B C multiplied by M Q minus N P is equal to A D M Q minus B C M Q minus A D N P plus B C N P. Now, let us compare the terms we obtained as the determinant of A B. We have A D M Q minus B C M Q minus B C M Q minus A D N P minus A D N P plus B C N P plus B C N P, and we can see that the remaining terms A M C N and minus NCM, they cancel each other. Therefore, we get determinant of A B is equal to same as the product of the determinants of A and B. Property 8. If all the entries of a row of A can be written as the sum of two quantities, then the determinant of A can be written as sum of two determinants. Let me illustrate. Consider A is equal to A plus K, B plus M, C plus N, D E F X Y Z. We see that the elements of the first row have been expressed as the sum of two quantities, each one of them. We claim determinant of A is equal to determinant of A, B, C, D, E, F, X, Y, Z plus determinant of K, M, N, D, E, F, X, Y, Z. This is very easy to see when we expand it along the first row of A, because determinant of A is equal to A plus K into determinant of E, F, Y, Z minus B plus M into determinant of D, F, X, Z plus C plus N into determinant of D, E, X, Y is equal to, we can write A into determinant of E, F, Y, Z minus B into determinant of D, F, X, Z plus C into determinant of D, E, X, Y plus K into determinant of E, F, Y, Z minus M into determinant of D, F, X, Z minus N into determinant of D, E, X, Y, and we can easily say that the first one is actually the determinant of A, B, C, D, E, F, X, Y, Z plus this is the determinant of K, M, N, D, E, F, X, Y, Z. Thus, the determinant of the matrix A can be written as the sum of two determinants. Let me now do a few problems. Find the determinant of one a square, one b square and one c square. We expand it along the first row. Therefore, determinant of A is equal to 1 into b c square minus c b square minus A into c square minus b square, c square minus b square plus a square into c minus b. Is equal to, if I take b c common from the first term, it is b c into c minus b minus a into c minus b into c plus b plus a square into c minus b is equal to, if I take c minus b as common, b c minus a c plus a b minus a b plus a square is equal to c minus b into, let me take c common from this. So, c into b minus a minus a into b minus a is equal to c minus b into b minus a into c minus a, which we can write it as a minus b into b minus c into c minus a. So, that is the determinant of this matrix. Let us explore another property. If in a matrix the ith row is replaced by the sum of ith row and jth row, then the determinant does not change. Illustration: consider A is equal to A, B, C, M, N P x y z. Let B is equal to the sum of first row and second row. That means, I am replacing row 1 with the sum of row 1 and row 2, which means that now B is equal to A plus M, B plus N, C plus P, and other rows remain same. It is M, N, P and x, y, z. Then the claim is that determinant of B is same as determinant of A. Why? Because of the property that if the row elements can be expressed as sum of two expressions, then I can write the determinant as the sum of two determinants. So, therefore, determinant of B actually can be written as determinant of A, B, C, M, N, P, x, y, z plus the determinant of the other components M, N, P, M, N, P, x, y, z is equal to determinant of A plus determinant of this matrix, which is equal to 0, since two rows are identical. Therefore, determinant of B is equal to determinant of A. A little bit more generalization. If the ith row is replaced by the ith row plus some constant times jth row, then also determinant of B is equal to determinant of A. Or if B is equal to A plus K M, B plus K N, C plus K P, M, N, P, x, y, z, then determinant of B is equal to determinant of A. This is true determinant of A plus M, K M, B plus K N, C plus K P, M, N, P, x, y, z is equal to determinant of A, B, C, M, N, P, x, y, z plus determinant of K M, K N, K P, M, N, P, x, y, z is equal to determinant of A plus, we know that if all the elements are multiplied by the same constant, then we can take the constant out. So, we can write it as k times M N P M N P x y z, and this becomes 0. Therefore, determinant of B is equal to determinant of A. Let us now do some more problems. Find the determinant of one B C A into B plus C, 1 C A B into C plus A, 1 A B C into A plus B is equal to determinant of 1 B C A B plus A C, 1 C A B C plus B A, 1 A B C A plus A B. Now, I have shown that if one row is replaced by the sum of that row and another row, then it does not alter the determinant. Since what we can say about rows, we can also say about columns. In a similar way, we can say if one particular column is replaced by the sum of that column and another column, then it does not change the determinant. Therefore, I can write that its determinant is 1 B C. Now, I am adding column 2 to column 3, B C plus A B plus A C. The operation is C 2 now becomes C 2 plus C 3. Column 3 becomes column 2 plus column 3. So, 1 C A, it is C A plus B C plus B A, 1 A B, it is A B plus C A it is C B, C B. Now, let us look at these elements. It is A B plus A C plus B C, it is A B plus A C plus B C, and this is also A B plus A C plus B C. So, all the elements of the third column are being multiplied by the same constant. So, its determinant is A B plus B C plus C A. If we take out that factor, what remains is 1 1 1 B C C A A B, then 1 1 1. And what is the determinant of this matrix? Because it has two identical columns, its determinant is 0, since it has two identical columns, therefore, the determinant of the original matrix is 0. Let us now solve another problem. What is the determinant of x plus y plus 2z x comma y, z, second element is y plus z plus 2 x y, and the third row is z x, z plus x plus 2 y. We need to compute the determinant of this matrix. What we will do? Step 1, we first add column 2 to column 1. C 1 becomes C 1 plus C 2. Then what we are getting? The matrix becomes x 2 x plus y plus 2 z x y, 2 x plus y plus 2 z y plus z plus 2 x into y, x plus z x and z plus x plus 2 y. Now, we replace column 1 by sum of column 1 plus column 2, column 3. Then what we are getting? It is 2 x plus 2 y plus 2 z x y. It is 2 x plus 2 y plus 2 z y plus z plus 2 x in y, and 2 x plus 2 z plus 2 y x z plus x plus 2 y. Now, we can see that in the first column all the elements are same. So, I can take it out is equal to, therefore, 2 x plus 2 y plus 2 z into determinant of 1 1 1 x y y plus z plus 2 x x y z plus x plus 2 y. This is still somewhat complicated. So, what we will do? We will replace now the second row with minus 1 times the first row. Just now we have shown that if one row is replaced by a constant times another row plus that particular row, then it does not change the determinant. So, what I am doing? I am replacing row 2 with row 2 plus minus 1 times row 1. Then what we are getting? Then its determinant is equal to 1 x y 0 y plus z plus x 0 1 x z plus x plus 2 y, of course, multiplied by 2 into x plus y plus z, as that is coming from there. Now, replace R 3 with R 3 minus R 1. What we are getting? Therefore, determinant is equal to 2 into x plus y plus z into determinant of 1 x y 0 x plus y plus z 0. Now, I am subtracting row 1 from row 3, 0 0 x plus y plus z. Now, if you observe, this is a triangular matrix, and we know that the determinant of a triangular matrix is the product of the diagonal elements. Now, these diagonal elements are x plus y plus z and x plus y plus z. So, their product is x plus y plus z whole square multiplied by x plus y plus z. Therefore, the overall determinant is going to be 2 into x plus y plus z whole cube. So, that is the answer. Notice that we did not explicitly expand it, because the terms are pretty long expressions are there. So, if we multiply this sum of 3 terms with another 3 terms, so this is going to be 9 terms, it will explode computationally. But what we did? We have used many properties that we have shown in the last class and this class very effectively to compute the determinant in a very simple way. Let me now take a numeric example. What is the determinant of 2, 7, 65, 3, 8, 75 and 5, 9, 86. Apparently very complicated, but it is not. I will look at these 2 columns and see how I can generate the third column. It is 65, here we have 7 into, and here it is 2. We know that 7 into 9 is 63 plus 2 is equal to 65. Similarly, 8 into 9 plus 3 is equal to 72 plus 3 is equal to 75, and 9 into 9 plus 5 is equal to 86. So, we can write it as 2, 7, 9 into 7 plus 2, 3, 8, 9 into 8 plus 3, 5, 9, 9 into 9 plus 5. Since the column is expressed as the sum of 2 elements, I can write it as the sum of 2 determinants is equal to determinant of 2, 7, 9 into 7, 3, 8, 9 into 8, 5, 9, 9 into 9 plus 2, 7, 2, 3, 8, 3, 5, 9, 5. This has 2 columns identical, therefore, this is going to give us 0, and this has the column 3 is 9 times the column 2, and therefore, its determinant is, if I take 9 out, it is the determinant of 2, 7, 7, 3, 8, 8, 5, 9, 9, and therefore, then we will find it has the same 2 columns. Therefore, its determinant is also 0. Therefore, answer is okay student. I stop here today. In this class, we have examined several properties of determinants and also we have solved several problems using those properties which made computation of the determinant simpler. In the next class, I shall see some more problems and also I shall go ahead with the concept of determinants, particularly Cramer's rule and solving of equations, etc. Thank you.